So this is a problem I found, and I figured I'd do one of each type, and so I'm reading this, and it talks about estimating the percentage of college students who cheat or plan on cheating, and not that I'm trying to say anything with this problem, it works. So some things when I'm reading these things, I've noticed that there's no mean. They aren't telling me there's a mean. They aren't telling me there's standard deviation. So that way I know this is about proportions. Okay, so that means I'm trying to estimate some population proportion, and I'm going to use that with my p-hat, my sample distribution, from my p-hat, and then apply that to the sampling distribution. So they're telling me that out of 560 college students that they sampled, 27 had or intended to cheat. So that's my p-hat. The 27% is my p-hat, and I'll write that as a proportion, a decimal, not a percentage. So what we're going to do is we're going to use that formula they show us in the book, that you take p-hat plus or minus your margin of error, and you get your margin of error by taking that z-score, that critical value of z that tells you how many standard deviations you need to go each side of the middle, or the mean. In this case, it's a proportion. It's the center of that distribution. Hopefully you watch that other video about sampling distributions. And there's many more on the web that if you didn't like that one. So what you do is you take, because we don't know the population parameter, that p, we're going to use p-hat as our estimate. And the standard deviation for proportions is calculated this way. You take your p-hat value, and you take that p-hat value away from 1, find the product of those, divide by the sample size, take the square root, and then you multiply by that critical value of z, and this whole side over here is our margin of error that we're going to add and subtract from that sample proportion to get a good estimate, get our confidence interval. Okay, so we know p-hat, we know the sample size, so we can have these values, we're going to be able to calculate it. This critical value of z is what we didn't know. So if we go look in the textbook, and this is the Moore textbook, in chapter 21 he gives us this little mini table. This is part of table B, a part of that standard normal curve table. And these are some pretty common confidence levels that crop up. Mostly they're usually 95%, but for the sake of testing you, we'll throw some different confidence levels in there. So what this tells me is if I want to be able to estimate a 95% confidence interval, I need to go 1.96 standard deviations either side of the mean. All right, and then we could 2. I know the book does it in example 2 where they use 2, and that's okay. I mean, that's an estimate. This gives us a little bit better estimate. So this z star value will be 1.96. Okay, and it just comes from table B. So I'm going to start filling in this formula. So p-hat's 0.27 plus or minus our 1.96 z-star number. And then to get the standard deviation, we take that 0.27 times 1 minus 0.27 divided by our sample size of 560. And one thing I'm hoping you get out of working through those examples in the book or in the exercises, both at Stats Portal and any extra you do out of the textbook, is the larger your sample size, the smaller your margin of error will be, because you're dividing by a bigger number here. Okay. So then we just got to calculate this. I guess what I would do on my calculator is, depending on what you have, I would take 0.27 times, let's see, 1 minus 0.27 is, if I'm doing my arithmetic right, is 0.73. Then I would divide that by 560, get that answer, take the square root of that answer. One easy way to do that is to raise it to the 0.5 power, or you can find your square root key. People have a problem with that sometimes. So once you've got that answer, then you multiply that by 1.96, and then that should be your margin of error. And I'll go ahead and calculate that and do this on the next screen. So the Google calculator told me that the margin of error is equal to that. So I've got the 0.27 plus or minus 0.0. I like to go one more decimal place than I originally have. I don't know why I do that. There's no rhyme or reason. So that would round to no, it would round to 0.7. What am I doing? So 0.037. Okay, and then we're just going to add and subtract it. So let's see. So 0.27 minus 0.037. You're going to get to see me do a little arithmetic here. So what's that? 2, 3. Yeah, you see me made a mistake with my arithmetic, huh? So that's 10. So that's 3. So 0.233 if I'm doing that arithmetic right. And I'm going to add it to get my upper bound. So what's that? 3.307. So we're 95% confident that the true proportion of, or true percentage of, I'm going to change this to percentages, the true percentages of college students, at least at that university, that intend to cheat is between 23.3% to 30.7%. Okay, and that's a confidence interval with proportions, and they're all basically like this. You know, you find the margin of error, and you add and subtract it, and then it's good to write a confidence statement. I read it aloud, but you always want to put it back in the context of the problem. So when on a test, when I say interpret the results, I want you to make some statement that says, you know, we are 94 blank percent confident that, and you fill in the what you're trying to estimate, what parameter you're trying to estimate is from the lower level to the higher level. Okay. So this is an example of a problem that's later on in chapter 21 in our sampling or our confidence interval chapter. And I'm reading this, and some things I'm noticing is that, well, they tell me the sample size, that's nice, but they also tell me the mean mathematics score and the standard deviation. So because they're telling the mean and the standard deviation, I know this isn't a proportion situation, this is a sample mean situation. So it's the same math, it's just that I'm talking about sample means, and the way you calculate the standard deviation is a little bit different. Okay, we'll do you do s over the square root of n. Okay, because we only know the sample standard deviation. We can't do much with that. I know anything with the population. So, but this is what we're going to do, and it's all basically the same setup. I've got a mean test score of 17.82. I know from what that work I did a minute ago that a 95% confidence interval requires a z-score of 1.96. And let's see, what's the standard deviation? 4.8 over the square root of 144. Isn't that nice? They picked a nice square sample number, huh? So then we just calculate this. We're gonna worry about the margin of error. On a calculator, I would just type in 1.96 times 4.8 divided by the square root of 144, which is 12, of course. So you don't have to write down all the symbols. So 1.96 times 4.8 divided by 12. So we go calculate that. So Google's telling me the margin of error is this number here, 0.784. So we're going to go and we're going to take this minus that number and this plus that number, and that'll tell us our lower and upper bounds. So I'm looking at this problem, and I'm looking at the decimal places that I've written down and calculated. I think what I'm going to do is I'm just going to use 2 decimal places, because that'll make a nicer number to work with than the 0.4. You know, so I'm going to ignore the 4 in the thousandths place. So I'm going to do 17.82 minus 0.78, and then I'm going to do 17.82 plus 0.78, and this will give me my lower bound, which I'll want to write first. Then this will give me my upper bound, which I'll want to write second. And then we'll want to write a confidence statement which says we're 95% confident that the true, I don't remember what this was about. So it's 95% confident that the true average math placement score is between whatever this value comes out to be, up to as high as whatever this value is going to be. Okay, and that's the confidence interval that estimates this unknown mean placement score. Okay, and it's that easy.